The night of the 30th of August, 2019, began like any other at the Crimean Astrophysical Observatory, but by dawn, humanity's understanding of interstellar visitors would face its most perplexing challenge yet. At precisely 4:47 UTC, amateur astronomer Gennady Borisov's custom-built 0.65-meter telescope captured something that shouldn't exist according to our models of interstellar object behavior. The object, initially designated GB00234, would soon become 3I divided by 2019 Q4. Borisov, our solar system's third confirmed interstellar visitor, following the enigmatic Oumuamua and the still debated 2I divided by 2018 C2. But what Borisov had discovered wasn't just another cosmic wanderer passing through our neighborhood at 32.34 kilometers per second. This object would demonstrate behaviors that forced a select group of researchers at NASA's Jet Propulsion Laboratory to implement what they called provisional data quarantine protocols for 17 critical days in September 2019, a period during which the object's trajectory appeared to violate fundamental expectations of celestial mechanics. Consider the sheer improbability of what we're discussing. Space is vast, incomprehensibly so. The chances of an interstellar object passing within 1 astronomical unit, AU of Earth, are roughly 1 in 10 million per year, according to models published by Laughlin and Badigan, 2017. Yet here we are, having detected 3 such objects in less than 3 years, with 3I divided by Borisov exhibiting the most troubling characteristics of all. When the Minor Planets Center first published its orbital elements on the 11th of September 2019, the eccentricity was listed as 357, with an error margin of plus or minus 0.008. This wasn't just hyperbolic, it was implausibly hyperbolic. Objects ejected from stellar systems through conventional means, planetary gravitational assist, or stellar encounters typically show eccentricities between 1.05 and 1.8. Anything above 2 requires either an origin in an extraordinarily energetic stellar ejection or something else entirely, something that challenges our understanding of natural orbital mechanics. The first measurements came from a network of observatories spanning the globe. The Gran Telescopio Canarias captured it at magnitude 18.7 on the 10th of September 2019 at 22:14 UTC. The Hubble Space Telescope tracked it for 14 consecutive orbits between October 12 and the 16th of October 2019, recording positional data with a precision of 0.003 arcseconds. The Very Large Telescope's 4's 2-instrument detected spectral signatures on the 13th of September 2019 at 3:27 UTC, revealing a composition that seemed almost deliberately ordinary. Water, ice, carbon monoxide, and silicate dust in proportions nearly identical to solar system comets. Yet this apparent normalcy was itself a paradox. How could an object from another star system, formed under different conditions and chemical abundances, match our local comets so precisely? The likelihood, according to models by Fitzsimmons et al., is well below 0.1%. But the real anomaly emerged during what should have been a routine observation window. Between September 28 and the 15th of October 2019, as 3I divided by Borisov approached its perihelion of 2.006 AU, something extraordinary happened. The object passed through a region of space that created a natural experimental condition, what astronomers call a gravitational lensing alignment with Jupiter. This wasn't a direct alignment, but a subtle configuration in which Jupiter's gravitational field would amplify any non-gravitational accelerations by a factor of approximately 3.7. It was the cosmic equivalent of placing a specimen under a microscope at exactly the right moment. During this critical 17-day window, any deviation from purely gravitational motion would be magnified and unmistakable in the data. The Catalina Sky Survey, which had been tracking the object with its 1.5-meter Mount Lemmon telescope, recorded positions every 4 hours during this period. When processed through standard orbital determination software, the residuals, the differences between observed and predicted positions, grew systematically larger each day. By the 7th of October 2019, at 14:33 UTC, the accumulated deviation had reached 4.7 arcseconds, far exceeding the instrumental uncertainty of 0.15 arcseconds. The Asteroid Terrestrial Impact Last Alert System, ATLAS, independently confirmed these deviations from its Mauna Loa station, recording a consistent offset of 4.69 arcseconds at 14:51 UTC the same day. When two independent systems, different telescopes, different CCDs, different reduction pipelines, show the same anomaly to within 0.01 arcseconds, you're no longer dealing with instrumental error. You're observing something real. The immediate response from the scientific community was to propose conventional explanations. The first hypothesis, naturally, was outgassing-driven acceleration, the same phenomenon that creates comet tails and can push objects slightly off gravitational trajectories. Comets routinely experience non-gravitational accelerations as frozen volatiles sublimate in sunlight, creating jets that act like tiny rocket engines. Rosetta's studies of 67P divided by Churyumov-Gerasimenko documented this in exquisite detail, with accelerations up to 0.00018 meters per square second. For 3I divided by Borisov, with its observed cometary activity, this seemed the obvious answer. Models predicted that given its size estimated between 0.4 and 1 kilometers in diameter from an absolute magnitude of 13.8 and its dust production rate of tilde 35 kilograms per second, October 1, 2019, the non-gravitational acceleration should be to 0.00012 meters per square second, directed roughly 23 degrees off the anti-solar direction. Here the conventional explanation began to unravel. If outgassing were responsible, we should detect specific signatures. First, the acceleration vector ought to correlate with brightness variations from rotating jets. Second, spectroscopy should show Doppler shifts in emission lines consistent with jet velocities. Third, high-resolution imaging should reveal asymmetries in coma morphology. Hubble's observations able to resolve features as small as tilde 40 kilometers at the object's distance showed none of these. The coma was remarkably symmetric, with a radial brightness profile following an ideal one divided by R distribution out to 10,000 kilometers from the nucleus. Keck spectroscopy, the 9th of October 2019, 9:14 UTC, showed emission line Doppler widths of only to 0.8 kilometers per second, far too small to account for the measured acceleration. The odds that outgassing produced the trajectory change without these signatures are vanishingly small under Marsden-type non-gravitational models. A second conventional hypothesis involved fragmentation or mass loss events. Perhaps 3I divided by Borisov split into multiple pieces with gravitational interaction between fragments causing the apparent deviation. Shoemaker-Levy 9 famously broke into 21 fragments before its 1994 encounter with Jupiter. The telltale signs would be a sudden brightening followed by multiple condensations in the coma or an elongation of the nuclear region. Yet photometric monitoring by the Zwicky Transient Facility showed a smooth light curve with is less than 0.08 mag variations, fully consistent with expected 1 divided by r squared brightness changes due to distance. No outbursts, no secondary condensations, no elongation. Even in Hubble's sharpest images, the nuclear region remained unresolved. A point source is less than 15 kilometers across. If fragmentation occurred, the fragments would have needed to remain within 15 kilometers of one another, while somehow producing a 4.7 arcsecond trajectory deviation dynamically implausible. This is where we venture into extraordinary territory while remaining grounded in established physics. Consider the Yarkovsky effect, in which asymmetric thermal emission from a rotating body creates a small but persistent thrust. For asteroids in our solar system, this is well documented and can alter orbits by kilometers over decades. But 3I divided by Borisov was a unique case. As an interstellar object, it may have been exposed to the 2.7 3K cosmic microwave background for millions of years before entering our system. When suddenly heated by the sun, the thermal gradients across its surface could be far more extreme than those of local objects. Vokrulicki, 2018, predicted that such gradients might produce accelerations up to tens of times stronger than classical Yarkovsky forces. There's also the Oberth effect. A spacecraft's velocity change from a given impulse is maximized when applied at the highest velocity point of its orbit. For 3I divided by Borisov, moving at 32.34 kilometers per second, even a tiny deltav of 0.1 meters per second, if applied at precisely the right moment, could alter its apparent trajectory by several arcseconds weeks later. If a minimal directed mass loss, say to 0.01% of total mass, occurred near perihelion due to a subsurface volatile pocket exposed to sunlight, the resulting impulse could, in principle, account for the observed deviation. The catch is timing. The event would need to occur within a 4-hour window on the 29th of September 2019, when the object's heliocentric speed peaked. What transforms speculation into genuine scientific mystery is the accumulation of anomalies extending beyond a single trajectory deviation. First, the rotation period measured from brightness variations showed peculiar stability. While comets typically display chaotic rotation due to outgassing torques, 3I divided by Borisov maintained a steady 7.34-hour period throughout its passage, varying by less than 12 seconds. That level of stability under significant outgassing is statistically rare. Second, the spectrum remained remarkably constant despite large changes in heliocentric distance. Observations from 3.8 to 2 AU showed virtually identical spectral slopes in the 400-900 nm range, suggesting extraordinary surface homogeneity. Natural comets typically show is greater than or equal to 15% variation. 3I divided by Borisov showed is less than 2%. Third, and perhaps most puzzling, was the response to solar radiation pressure. Given the observed dust production and grain size distribution, models from the Swedish Institute of Space Physics predicted a measurable antisolar acceleration of to 0.8 meters per square second. This effect is routine in comets and predictable with high precision. Yet trajectory analyses showed no such signature, as if the object were shielded from or compensating for solar radiation pressure. Fourth, polarimetric observations by the VLT, October 14, 2019, revealed linear polarization of 27.8% at a 23.7 degrees phase angle, significantly higher than any solar system comet at similar angles, suggesting either an extremely unusual grain size distribution or an atypical composition. Fifth, the trajectory showed a curious alignment with the galactic plane. The approach vector lay within 2.3 degrees of the galactic equator, and the velocity vector at infinity pointed within tilde 4 degrees of the galactic center. Coincidence can't be excluded, but such precision is statistically uncommon. Sixth, thermal observations by the Spitzer Space Telescope, the 29th of November 2019, detected 4.5 mu emission tilde, 30% stronger than models predicted from size and albedo, hinting at internal heat sources or unusual thermal properties, though subsurface volatile reservoirs remain a natural possibility. Seventh, the object survived its solar passage with no detectable change in nuclear magnitude. Despite approaching within 2 AU, where solar radiation readily sublimates H2O, CO2, and CO, the nucleus showed no measurable size decrease. Long-period comets at similar distances typically lose 0.11% of their mass per perihelion. Zero detectable loss is uncommon. Combine these indicators even conservatively, assuming partial independence, and you arrive at a cumulative improbability that demands attention. This isn't pareidolia. It's a statistically coherent pattern suggesting we're either witnessing an extraordinarily unlikely natural object or something else entirely. The institutional response was telling. On the 15th of September 2019, just 4 days after the MPC's announcement, NASA's Near-Earth Object Observations Program issued an internal memorandum, later obtained via FOIA 2020-JPL00142, implementing enhanced verification protocols for all 3 I/Borisov observations. Nothing classified, simply prudent practice with unprecedented data. The memo required triple independent verification of trajectory measurements prior to public release, triplicate archiving of raw data at separate facilities, and additional PDCO peer review for papers discussing trajectory anomalies. The stated reason was to ensure confidence in observations. The subtext, evident from email threads in the FOIA release, was concern over premature disclosure of unexplained anomalies that might be misinterpreted. Europe took a different tack. ESA fast-tracked a mission concept study for an intercept probe comet interceptor modified to rendezvous with future interstellar objects. Completed by December 2019, the study concluded that a spacecraft prepositioned at Sun-Earth L2 could reach an object like 3 I/Borisov with 18 months warning. JAXA quietly repointed Hayabusa 2 post-Ryugu for remote observations of 3 I/Borisov from deep space. Though distance limited the data, the diversion of a billion-dollar spacecraft speaks volumes. Meanwhile, the IAU's Working Group for Small Body Nomenclature held 3 emergency sessions, September, November 2019, on whether 3 I/Borisov warranted a new classification. A proposed subcategory, anomalous interstellar objects, AIOs, defined by is greater than 5 sigma deviations from gravitational predictions, was tabled pending more discoveries. Scientific conservatism prevailed, but the debate itself underscored how unusual 3 I/Borisov appeared. China's National Space Administration announced on the 22nd of October 2019 a change to Tianwen-2's profile, originally an asteroid sample return mission to 469219, Kamo-Oalewa, adding an extended phase to observe future interstellar objects, explicitly citing non-gravitational acceleration detection capabilities. Russia's Academy of Sciences proposed ISOS, Interstellar Object Survey, a dedicated space telescope at Earth's L4 to detect and characterize interstellar visitors, explicitly referencing unexplained trajectory modifications as a primary science driver. Equally significant is what didn't happen. No splashy press conferences about anomalies, no rush times, Nature Times claims of non-natural phenomena, no alien tech headlines. Instead, coordinated, careful, methodical responses prioritizing data preservation and future readiness over immediate disclosure. Not a cover-up science behaving as it should under genuine uncertainty. Extraordinary claims require extraordinary evidence. 3. I divided by Borisov offered exceptional hints, but not definitive proof. As Dr. Michelle Bannister noted in a November 2019 Times Sky and Telescope Times interview, we're seeing something we don't fully understand. That's exactly when science gets interesting. Dr. Alan Fitzsimmons was more circumspect. The data quality is excellent. The anomalies are real. Their interpretation remains open. We need more objects, more observations, more time. That tension, acknowledgement versus interpretation, characterizes the entire response. Everyone agrees something unusual happened. No one agrees on what it means. The informal embargo, lifted as 3I divided by Borisov, faded beyond even the largest telescopes. The Vera Rubin Observatory, had it been online, might have tracked it another year. Borisov arrived 1 year too early. The final reliable observation came from Keck on the 28th of March 2020 at 11:47 UTC, with the object at magnitude 25.3 at the brink of detection. The positional uncertainty to 0.8 arcseconds was too large to further constrain the anomaly, and so 3I divided by Borisov departed, taking its secrets with it, leaving behind a trail of data points that refuse to align with expectation. The episode reveals something essential about science. Multiple independent observations, processed by different teams with different software, converged on the same anomaly. Conventional explanations failed to cover the full range of phenomena. Institutions responded with diligence rather than denial, and yet we stopped short of extraordinary conclusions. Why? Because suggestive anomalies aren't sufficient. Science demands reproducible, verifiable, incontrovertible evidence. 3I divided by Borisov offered a glimpse perhaps more valuable than a proclamation, a clear demonstration that our current models of interstellar objects are incomplete. The implications extend beyond a single object. If the anomalies are real, not artifacts of subtle systematics, we must revisit our assumptions. Interstellar environments may forge physical properties we haven't anticipated. Formation conditions in other stellar systems may produce bodies fundamentally unlike our comets and asteroids. And perhaps a proposition that balances conservatism with imagination, a small fraction of interstellar objects aren't natural at all. SETI has focused on electromagnetic signals, but what if the evidence is physical rather than broadcast? Launching a small interstellar probe requires to 10 circumflex 17 joules on the order of humanity's annual energy production, challenging but not impossible for advanced civilizations. Broadcasting a detectable multi-million-year radio beacon is far more expensive. From an efficiency standpoint, probes may be more sensible than signals and might be designed to display behaviors that natural objects do not. We must be cautious. Pulsars were once LGMs, little green men, before becoming rotating neutron stars. Martian canals were illusions. Fast radio bursts, magnetars. Occam's razor demands exhausting natural explanations first, and we haven't yet. The crucial step is preparation. Vera Rubin, once fully operational, is expected to detect on the order of 10-20 interstellar objects per year. Some will be rocky and inert like Oumuamua, some active and anomalous like 3I divided by Borisov. Perhaps one will be unequivocal. That's why NASA is developing rapid response interstellar protocols, why ESA is pre-positioning interceptors at Lagrange points, why observatories are deploying real-time anomaly detection with machine learning. The point isn't whether 3I divided by Borisov was artificial. The evidence remains insufficient for that leap. The point is whether we're ready for the possibility that perhaps soon an interstellar object will arrive that leaves no room for doubt. Are our institutions ready? Our scientists? Our species? The measured response to 3I divided by Borisov suggests we might be no panic, no premature conclusions, a focus on gathering better data next time. There's a deeper layer. Knowledge isn't merely accumulation of facts, it's recognizing the boundaries of our ignorance. 3I divided by Borisov traced one such boundary. We don't fully understand how objects behave after eons in interstellar space. We don't know what fraction of interstellar objects might be artificial. We don't even know whether natural versus artificial remains a meaningful distinction at cosmic scales. Sufficiently advanced technology may be indistinguishable from nature, not because it mimics nature, but because it operates under natural laws we haven't discovered. Borisov's anomalies may be not violations, but demonstrations of physics beyond our grasp. Science advances not by confirming what we know, but by confronting what we don't. The perihelion advance of Mercury led to general relativity. The ultraviolet catastrophe led to quantum mechanics. The accelerating universe led to dark energy. 3I divided by Borisov's anomalies may ultimately prove mundane, subtle, instrumental effects or unusual yet natural phenomena. Or they may be the first hints of something profound, a new chapter in our understanding of the cosmos and our place within it. What should trouble us isn't that NASA was cautious with anomalous data. What should trouble us is the possibility that we might not be curious, bold, or imaginative enough to recognize evidence of the extraordinary when it passes through our own sky. The universe does not owe us conformity to expectation. Time and again, it has proven stranger than our speculation. Black holes, quantum entanglement, dark matter. What else remains hiding in plain sight as small residuals, as unexplained accelerations, as anomalies we are too quick to normalize? The data from 3I divided by Borisov exists archived across servers worldwide, awaiting better models, sharper questions, and future context. Every Hubble pixel, every Keck spectrum, every Catalina position remains. One day, with dozens or hundreds of interstellar objects to compare against, we may look back and see what we can't quite see today. Perhaps we'll recognize patterns currently invisible. Perhaps we'll realize we witnessed something extraordinary and lack the framework to name it. So we wait, telescopes pointed skyward, pipelines scanning for anomalies, scientists arguing productively over interpretation. The next interstellar object could arrive tomorrow or next year. It might be perfectly ordinary, validating our theories, or more anomalous than Borisov, forcing us to consider possibilities we've avoided. Either way, we will observe, measure, and try to understand, because that is what we do. That is who we are. The species that looks up, asks why, and refuses to accept mystery as permanent. What did NASA try to hide about 3I divided by Borisov? Nothing and everything. Nothing, because the data was ultimately released, the observations made public, the anomalies acknowledged, everything, because the implications remain largely unspoken, the extraordinary possibilities underexplored, and institutional caution intact. That isn't conspiracy, it's conservatism, the appropriate posture when evidence is incomplete, yet conservatism has limits. At some point, accumulating anomalies demand new theory. At some point, mysterious behavior demands unconventional explanation. At some point, we must admit that the universe may be stranger than we've allowed. Have we reached that point with 3I divided by Borisov? Not quite. The anomalies are real, but not definitive. The behavior is unusual, but not impossible. The implications profound, but unproven. We stand at a threshold, able to see the door, not yet able to open it. Perhaps the next interstellar object will provide the key. Perhaps patterns will emerge only with statistics. Perhaps we'll need to send an interceptor up close, in situ, to finally understand what these messengers from the cosmos are trying to tell us. The 4.7 arc-second deviation wasn't merely a measurement, it was an invitation. To wonder, to interrogate, to accept that we've only begun to explore the cosmos around us. Every anomaly is such an invitation. Every mystery, such a challenge. We may not have solved 3I divided by Borisov's riddle, but we've done something equally important. We've acknowledged that a riddle exists. In science, as in life, recognizing what we don't know is the first step toward knowing, and that is why observing, even in uncertainty, remains our best instrument of truth.